Hi everybody, good morning. Thank you so much for coming. Where I'm from, I'd be standing alone in this room, or in fact, I'd probably just lie down and go back to sleep. But thank you. Uh, so my name is Dina. We're going to talk today about self-aware applications. It's not going to be as creepy as it sounds. It's going to be about this mantra that I'm trying to push forward lately, and that's monitoring your own applications, self-monitoring and self-diagnosing. That's the new thing here. Monitoring is not new, of course, on production. So let's start. I always like starting my talks with a little motivation. So I'm going to do a little motivational talk. Then I'm going to present the master plan of how I'm going to try to conquer this self-diagnostic mountain. And then after all the introductory hand waving, we're going to embark on 4 demos through which I will try to show you some examples of what's possible to monitor and diagnose on your production applications. So, why should we even monitor? I think this is, fairly correct to say that we all probably agree that we must monitor our applications. This is especially obvious for anything at scale. If you're developing servers, you have to be on top of things. You can't wait for the users, to call you, tell you anything is wrong. You can't wait for for actual negative value to happen. You have to be able to stop the things before they cause damage to your clients. And since we're talking about scale, about large systems, you obviously can't do that manually. It has to be automated. But that's, again, that's the obvious stuff. What I want to add here, my 2 cents, are that I think it's just as important to monitor your simple desktop applications. And in a sense, from my experience, the situation there can be much worse. Because while you usually have access to your servers and you can actually do the monitoring, when you ship your desktop applications to the clients, you have millions of clients, let's say, you usually don't know what's going on after they install it. You don't control the system, you don't know what's installed there, which patches to the OS are there, if there's other software getting in your way. You don't know anything that's going on. And it's not until the clients call and, get upset about something bad that's going on, or I'm not going to renew the subscription or whatever, and then you have nothing to do because you don't know what's going on there, you don't have any visibility into the system. You can't recreate it in your development, and it's a problem. So now that we've established that we need to monitor whatever it is, the kind of application that we're developing, why should we do it our own? After all, there are plenty of monitoring and profiling solutions out there. So I didn't write this in the slides, but personally, I think that investigating performance is interesting. So there's, that upside. But on a more practical note, when you implement monitoring, excuse me, yourself, this is the major advantage that you get. You can specialize and customize your monitoring to your specific business needs. It's not just going to be that general CPU or memory or I don't know what else is there, you can monitor your specific queues, you can monitor your specific critical components, you can monitor what really matters. And another interesting thing that you get from this is that the diagnostics flow from ground up. And what I mean by that is that you don't have to wait for this loop of data to arrive back to you. You don't report to some dashboard, to some server, which reports to some dashboard, which reports to some, I don't know, telephony system, which is gonna, then wake you up in the middle of the night saying, hey, something happened like an hour ago, please go look at it. No, the application monitors itself It gets all the data, it knows what's going on, and it actually becomes self-aware, allowing it to possibly diagnose, or at the very least, get more data that will help you diagnose the problem later. And lastly, it seems that the community is kind of converging on this DevOps state of mind, so you can't, just be left behind. But of course, that's for all the good reasons that we mentioned just now. So monitoring is cool. Okay, so we're sure that we want to monitor, and we're sure that we want to monitor, with our own bare hands. How do we go about doing that? Because obviously we can't attach a profiler or a debugger to our production system. It's just going to be too costly. Both, by the way, overhead-wise, of course, but also, financially, because you just can't buy profilers and debuggers to put in each and one of your machines. So what I suggest here is to use a hierarchical monitoring scheme. So we'll use the cheapest tools available to monitor all the basics. So that's those generic stuff that I talked about before. CPU, memory, disk, and of course, your specific business needs stuff like queue sizes, maybe timeouts, requests that your application gets, whatever. These would usually be numerical values that represent some resource consumption. There are a few tools which are available to you to do that. The first is performance counters, which are like these objects spread out through the Windows system, which, how to report numerical values that represent whatever is going on inside. If you don't like performance counters, you can resort back to just using plain Win32 APIs. And of course, for your own specific components of the system, you'd have to probably measure yourself or output, queue sizes again, or whatever yourself. Then, if there are some more rare events that happen, such as exceptions or maybe some deadlocks that you might detect, you can try to put a little more effort into investigating the problem and use slightly less lightweight tools that provide more information. So for that, you could, for example, use ETW, Event Tracing for Windows, which is also spread out through the Windows system. It's actually a structured logging framework, which provides quite a lot of information about what's going on. And the overhead of using that mostly depends on the amount of data that you want to get and on the frequency of the events. So it really is up to you how much overhead it's going to introduce into your application. And there's also CLRMD, which is an open source library provided by Microsoft, which provides a debugger-like API, which allows you to attach to your applications and traverse memory, look at threads, and so on. And so again, the overhead depends on how much heavy processing you're going to do. So it could be used as a medium overhead tool, as a lightweight tool, whatever you do with that. And if worst comes to worst, you can, really take out the big guns, use debugging APIs, use profiling APIs. If you really want to, you can hook some stuff in your application. And again, the overhead of hooks, of course, depends on the amount of work that you do inside the hook. We're not going to talk about any of these today because we don't have time and it's way too complicated. And I really think this is a very last resort, because even the official documentation of the CLR profiling API says it's not suited for production if you care about your application's latency, performance, or whatever. So we're not going to do that today, but just know that it exists. You might find that suitable for some cases. Let's start. Our first demo for today is going to be profiling and diagnosing CPU. Now, it sounds pretty basic, but even that alone can give a huge benefit to your application. Because again, and I'm having in mind desktop applications because that's what I have most experience with. It happens to us quite a lot that customers complain that CPU has gone up and and it's hogging our machines and it's all bad, and it kind of stops after a while, and we don't know what causes that. We don't know how to reproduce that. Even the customers don't know what exactly they did that caused that. And so imagine that your application could detect that it's using high CPU, like right now, right this moment, and start profiling itself and just like write in the log, well, I was doing this function for, this long and the other function for that long, and just ship the logs to production, and there you have it. You have a solution. So that would be pretty cool. So how does that fit into our master hierarchical plan? Well, quite easily. What we can do is that we can monitor CPU using performance counters, for example. These are, again, just numerical values. It doesn't introduce any overhead for any practical means. So we could define like a condition, something along the lines of, if our application uses more than 80% CPU over, say, 10 seconds, then this is not cool. We're going to start profiling. Specifically, what I'm going to show you is how we can profile our application using ETW, which can actually provide us real-time call stacks of what's going on in our application using an open source project called LiveStacks. There's a link on the slide. And it's just going to output us call stacks with percentages, just like a profiler would. We can, paint flame graphs if we want. We can report the hottest path or whatever works for us. And according to this information, we can even suggest recommendations about what to do. And when I say we, I mean the application to itself. If you're wondering what the application could do with this information, so here are a few examples. For example, if your authentication controller is suddenly overworked, maybe you're being attacked, that's a possibility. Or if some computational component in your application takes a lot of CPU, you might consider scaling up. And what would be even better and ideal is that if the scale would happen automatically according to this information, which would be pretty cool, I think. At the very least, if you don't have anything smart to say, you can just write down all the information in your log or whatever system that you have and ship it back to the developers so they can look at the information later and try to diagnose it better. Okay, so let's have a look. We're not going to do anything live today, so I recorded the demos in case something doesn't work and because we don't have a lot of time. So I have this application that I wrote. It's a website about cats. And what you can see here, I'm about to play that, but here I have a graph of CPU usage, and this is my website, and I'm going to do something. And let's look at how CPU works. Go away. Okay, you're going to see what's important in a second anyway. So I'm trying to log in. And there's a CPU spike. Something is going on. I don't know if it makes sense for logging in to take 100% CPU. It sounds pretty fishy to me. I don't know. And anyway, after a while, it goes back down. So that's an interesting behavior, and we would like to understand what causes it. Let's look at the code and then look at the results. So I have my Visual Studio here, and we're not going to go into too much detail because frankly there's just not enough time to do that. So I will try to show you the general scheme and the interfaces without diving deep inside the implementations. So we have our CPU, where is it? We have our CPU monitor, okay? And it has a bunch of definitions here, which will come back later, and that's pretty much it. But this CPU monitor inherits from event stacks monitor. You can understand from the name, the CPU monitor is going to give us call stacks of what's going on in our application. And the event stacks monitor itself is a type of a monitor. And this is where we'll start our code. So we have this concept of a monitor now. Like, I'm not sure that design-wise this is the best code, so I don't go copying it exactly into your production. But think of it as a general idea. So what does this class entail? This class describes the general concept of doing some lightweight monitoring using performance counters. So that's the performance counter that I'm going to listen to. And then waiting for a certain number of violations above the threshold for that performance counter. And if that happens, sorry, where is that? Yes. And if we pass this certain number of violations, we just open up the intensive sampling mode and start doing the actual processing. So in the case of CPU, we would use the processor time performance counter, and we don't want it to be over 90% for 3 violations, which is about 10 seconds, if I remember correctly. Now, what we see here, is that we start the intensive sampling. And in the base class, this intensive sampling does nothing. So in the event stack monitor class, we implement the logic that collects call stacks on intensive sampling. This is done using ETW. And what we can see here is, and again, I'm going to go over it very basically. We create a live session which listens to the CPU, which samples the CPU for the commands that it implements. And it simply waits for a while for the intensive sampling duration, which again, if I remember correctly, is about 5 seconds. Yes, it's 5 seconds. And all this is done using the live stacks code, which you can find online. And after those 5 seconds, we stop the ETW session, the live session, and we simply have access to this property here, stacks, which simply, and the top stacks, which simply provides the most CPU intensive stacks which were recorded during this time. Now, another thing that this class gives us is an event which tells us that an ETW event has occurred. And it allows us to get even further information about what's going on. So in the case of call stacks, though, there's nothing else that we're interested in. So again, I'll recap. This class, event stack monitor, allows us to listen to certain ETW events, collect the call stacks from these events, and aggregate some more or calculate some more data according to whatever it is that we want to do. And in the case of call stacks, of profiling CPU, we don't need any additional data. We just keep the call stacks. And again, after we're done with the intensive mode, we just write down these call stacks to our log file. So let's open such a log file. This is a log file I collected from the application. And specifically, when I did that, I separated the logs of the CPU monitoring, the allocation we're going to see later, of all the demos that we're going to see today, so that they're not intertwined. But in a normal usage, they would probably be somewhere together, and you'd have to kind of search the stuff. So here we can see sampling, timer, we have high CPU, we have some violations, and so we start collecting stacks. And after we're done collecting the stacks, we just write them to the log. And we have all sorts of CLR stuff and MS-core-lib stuff, of course, and then we finally get to our own code. That's our code that we can understand. And it would seem that there's a function called goodHash, which is being called. And all of this comes from the login controller. And if I go back to the login controller, which is right here, then what I can see is that if an email ends with Gmail, and remember that that's what I used in the recording, then we start calculating hash values. And that obviously takes a lot of time, and in my case it took 100% CPU for several seconds. So, mystery uncovered. Okay. Our next demo is going to be similar, but a little different. This time, we're going to look at GC performance problems, or rather, problems in our code that might lead to GC degradation, GC performance degradation. So, for this demo, what we're going to do is that we're going to monitor rate of allocations. And the reason I'm going to monitor rate of allocations and not time in GC, for example, is that I think it would be kind of too late. Because if we're already inside GC doing too much GC, it's like past the problem has already occurred. And I want to try to recognize the problem before it happens. So I'm going to look at rate of allocations, and again, doing the same scheme of if I have too many allocations over a period of time, then let's get some data. And what is this data that I'm going to collect? This time we're going to look at ETW events from allocations, which will provide us information about the size of allocation and types of allocations. And that would provide me, that would allow me to calculate some information about the types which we allocate and where they're being allocated, as you will see soon. And of course, just to mention, this is very important because if we get too much GC, our server might start, failing responding to requests fast enough. But I want to mention those desktop applications again. Because GC hiccups in UIs are very, very, very annoying to users. If your application starts pausing because of that, it's a critical usability problem. So just wanted to mention again how we shouldn't ignore our desktop applications. So we can get a lot of information from ETW, as we'll see in a moment. And if we want to get even more information, we can actually attach CLRMD and start looking at the different generations, at the segments of memory, what's actually resides right now inside our memory. So let's have a look. Again, we'll start with a video. The same thing, this time, here you will be able to see the rate of allocations. And so I'm going to go to the About page, and it will seem that going to the About page causes quite a lot of allocations in our cat website. So, as before, it's something that we'd like to diagnose. Let's now go to our Allocation Monitor. And you will see that it's similar to the CPU monitor in the sense that it also inherits from the Event Stacks monitor. But this time, of course, it looks at the allocated bytes per second performance monitor. And the ETW event that it's interested in is allocation tick. So again, let's remember what Event Stacks Monitor is going to do is that it's going to listen to the allocation tick event. It's going to collect call stacks from this event, which means that we'll get call stacks of when allocations are happening. Only this time, we're also going to register on the event occurred event and do some bookkeeping. So as you can see, we have this GC allocation tick trace data class, and it gives us information about the allocation amount, about the type name that we allocate. And so it's fairly easy for us to simply keep a dictionary with information about the types that we allocated during the intensive sampling and how much of this type was allocated during the intensive sampling. And of course, after we're done with all the collections, we simply print all of this data to the log file. So we print the most allocated types. Remember that we print the call stacks from the event stacks monitor. And another thing that we can do, and this is a good time to introduce CLRMD, is to also display what happens in the heap right now. So we got all these allocations from the past 10 seconds, or 5 seconds, I'm sorry, but we also want to know what's going on in the heap right now, because these allocations don't give me any information about, like what was there before and what happened in the meantime. So what we can see here is how we use CLRMD to attach to our process. This is our process right here. And basically you can see that it gives a very easy API to accessing the heap, getting size of the total heap, getting size by generations, going over all of the heap objects, getting their type, getting their size, and we can aggregate that into a table which matches the type to the total size of memory that it takes. And so all of that is printed into our log file. So let's look at it. This is our allocation log file. At first everything was good. Scroll down faster. Everything was good. Suddenly, allocations start occurring. And we have call stacks from the call stack monitor. So this is the call stack from where most allocations happened. And so again, we have all the CLR stuff, mscorelib, so on and so forth. And this is the first time that we encounter our own function. And it comes from the about controller. Before we go to the about function, before we go look at the code, let's just see the heap breakdown. It's okay, good. So we have this statistical data from the recording. We have the total allocations, and we can tell which types were allocated the most. And it's interesting to see that we had a lot of strings allocated. That was the most allocated data type. And we can also see the heap breakdown, which shows us, incidentally, that the type which takes most memory is also a string. If we go back to our code now, to our home controller, to the about action, we can see that it does some major XML processing, which obviously causes a lot of strings to be allocated. So again, mystery solved. Of course, this is a simple demo just for the sake of the stock, but I do think that you'd be able to get real information about your own code, and knowing the code and knowing what's going on there, of course, is going to help you figure out what the problem is. Doesn't work. Okay. Next demo is also going to be about memory, but about a much more feared scenario, and that's memory leaks. Or in fact, maybe not just memory leaks, but even just like high memory usage above a certain threshold that you don't think your application should pass. And how are we going to do that? Again, very similarly, just monitor the total memory size, recognize that we have passed the thresholds which are allowed, and then try to diagnose. Now, specifically for memory usage, there's not much you can do with call stacks because it's all about, what's going on in the memory right now. It's not about allocations which are happening, it's about a certain state. We have arrived to a state in our application where there is lots of memory usage. So what can we do still in this case? Well, the most common thing people do when they try to diagnose memory leaks or generally high memory usage is one to look at what's going on in the heap right now, very similarly to before, just write the heap breakdown. And the second is try to take several snapshots of the heap with a few seconds apart or whatever and compare them. And we can do that very similarly to what you just saw using CLRMD. If you want to get even further information, you might be able to correlate this data still with the allocation information that you want to collect, but we won't do that right now. So let's see. Again, we start with a video of our memory leak. Again, our wonderful website. This time what we see in perfmon is the size of the memory, and I'm going to try to register to our website. So far memory looks okay, and I try to register, and let's see what happens. Okay, that's still okay, doesn't mean anything. Let's wait. See how it turns out. Okay, it gets higher, and well, we won't end to the end of the video. I'm gonna scale it so that you can see. It's gonna get even higher later. So it looks suspicious, right? Let's see what our code can do with that. So we'll open the memory leak monitor. Here it is. It's going to be fairly simple. So this time, as I said, it's not going to be an event stack monitor because there are no call stacks that we need to collect for high memory usage. So it's just going to be a simple monitor which waits for this threshold based on this performance counter. And what it's going to do in its intensive sampling mode is just take several snapshots of the heap and then analyze them and find the differences. So again, this is very simple. We do a loop, wait a few seconds between each iteration, and attach to our process just like before and get the heap snapshot, again, just like before. Now note this, we need to, well, it's better for us if we collect before and wait for all the finalizers to be done, because we don't want any misleading information in our heap snapshot. So we do that before, but other than that, it's very, very simple. And after we're done taking all of the snapshots, we simply go over them. In our case, I think it's 3 snapshots. Just go over them and calculate the difference. So what is this heap snapshot? The heap snapshot is basically a dictionary, which tells us the total size of each type on the heap and the number of objects of each type on the heap. And the way we get it is, again, just like before. We traverse the heap, we get the types, we count them, we sum the memory, and we put it in our dictionaries, size by type and count by type. And so later very easily, once we have these two snapshots, we can simply calculate the difference between them. What was allocated and what was freed in between. And just write all of that down into the log file. So let's see what we have here. This is our leak. And again, at first everything was fine. And then a violation occurred because we used too much memory. And so we got these snapshots and these comparisons. And this is a little more complicated because, and specifically in my case, what you will see is that the number of byte arrays has increased very significantly between our snapshots. And this is something which is very hard to diagnose just by looking at log files without, knowing the code. If this had been a concrete type from your application, of course it would be very easy. In this case, it's simply a byte array. But I know the code, and I wrote it, and I know where I allocate byte arrays. And specifically, it happened when we tried to register, right? So it's the account controller. And I happen to know that somewhere here, yes, somewhere here, there are allocations of byte arrays. And it would seem that these byte arrays are saved into a static list, which of course causes a leak whenever I try to register and check the password of the person who tried to register. So again, this is a slightly more contrived example in the sense that we have byte arrays, but when you work with your own application and you know what's going on, it's much easier. On to our last demo. So our last demo is going to be of a deadlock. Now this is a little more complicated than finding a memory leak, or rather, it's not more complicated than finding a memory leak, but memory leak is very straightforward. When you want to diagnose a deadlock, it's not clear that you have a deadlock. So I have a few suggestions on how to diagnose that you might have a deadlock. For example, if your application suddenly uses like very little CPU, then you might be blocked. Or if your requests start timing out, then maybe the thread that's handling them is blocked. Or the other way around, maybe suddenly your thread pool is opening more and more and more threads because, threads get blocked and they need to process requests. So all of these might suggest that we have a deadlock, and if you are afraid that you might have a deadlock, then you can attach CLRMD, as we'll see in a moment, and start traversing threads and creating weight chains and detecting whether you might have a deadlock actually. Now in this case, I'm not sure there's anything you can do about it, but even just report to the development so that you can fix it in a later version is also a good enough solution, the way I see it. So let's see. This time, and what we see here is CPU usage. Play. We're going to go to the contacts page, I think. Go to the contacts page, yes. And I won't make you wait throughout the entire video. You can see that nothing is happening. CPU is 0. I think we're stuck. So let's see how we could detect that in our application. Our deadlock monitor. So we're not going to do all the logic about, listening to CPU or threads or whatever. You've seen enough of that. Just want to quickly show you the APIs which are available in CLRMD that would allow you to diagnose a deadlock. So we have the deadlock monitor, and just every once in a while, it's going to traverse all the threads and check for a deadlock. So this is the major thing here, and we're not going to go over like the logic that builds the weight chain graph. That's an algorithmical issue. I'll leave you to it. What I want to show you is, again, I attach to my process. I have access to all of these threads, and these threads have thread IDs, which I can access, and they have call stacks, where is it? And they have stack trace, which I can get. And they have a blocking object property, which tells us what these threads are waiting for. And so once I have all of, and even the reason they're waiting for it. And so once I have all of these APIs, it's very simple to traverse the threads and find cycles in the weight graphs. So let's look here. I already opened the log file. The interesting part, and it would seem that indeed we have some deadlocks detected, and it displays the thread and the call stack, and we can see that it's in home controller process details. So we go to the home controller, to process details. Here it is, and we can see that there are two locks here, first and second, and we call process details again from a different thread. This time the first is the second and the second is the first, and we have a deadlock. Cool. Doesn't work. Okay. So that was our last demo for today. These are just 4 demos that I thought of. Obviously, there are more scenarios possible specifically for your business needs. Just like 2 more examples of what you could do. You could monitor for heap fragmentation because the CLR is not going to compact the large object heap for you because it takes a lot of time. So unless you specifically call it, it's just going to stay the way it is. And so if you monitor, for example, the heap fragmentation, you can do an educated decision on whether you want to call a large object heap compaction or not. So that's an interesting idea. Another thing I want to mention here is that all of our demos were about .NET applications, but you can actually use ETW to try to diagnose native leaks as well by monitoring where allocations are made and getting call stacks for that. So that's also an interesting idea that you can go for. And again, I'm sure you can think of much more. So it looks like everything is like all perfect and dandy, right? And the pros are obvious. You get visibility into your applications. You can scale this solution, which is pretty cool. But still, of course, there are a few drawbacks that we need to think of before we continue. And the first is, of course, the complexity. You write more code, you introduce another component to your application, and it means that your application becomes more complex. Now, you could reduce this risk, though, by implementing all this logic from an external watchdog process. None of the things that we saw has to be done from within the application. ETW is collected machine-wise, performance monitors as well. CLRMD, you saw, we passed it the process. We could have easily passed another process. The only thing that might be problematic is that we called GC collect at some point. So, it might be a little harder for you to diagnose the leak, but it's possible. Next problem is, of course, the overhead. And I actually have two examples from real life about this, where it gets especially hard with slow and weak machines. At first, I did all my demos on an Azure VM, and it was all fine. But then I started running it on my laptop, on my VM, and pretty much I had to really decrease all the CPU thresholds because just the monitoring code itself was using too much CPU on my machine. And then about 2 months ago, we had a problem with a client where one of our processes was taking too much CPU, and we attached a profiler only to find out that a lot of time was taken by our code, which was writing down stacks. So what happened was that our code diagnosed that it was using too much CPU, And so it started, writing stacks to the logs, and it only made the problem even worse. But well, that was a laptop with a single core, so we don't see that a lot of that these days. So I don't feel like really bad about it, but remember that it's something you need to think about. And of course, it requires additional development. But it's up to you or your manager to decide whether it's worth it. Is that it? Sorry, yes. Perfect timing. I was surprised. So what did we see today? We saw that it's very important to monitor your applications, whether it's a server or desktop, whatever kind of deployment or application you have. We saw how to tackle this problem using a hierarchical monitoring scheme. And we saw 4 scenarios where it can be useful. All the demos are in line, so you can try to run them yourself. Just take a better machine than what I have on my VM. Thank you.